So then we are ready to start, and I want to introduce our first speaker, who is Helen Dew, who will give a short introduction on the FTI project.
Thank you so much, Annemie. And I must say again, welcome to everyone who is attending the webinar. We're very happy to see that so many people wanting to learn more about plasma technology. We have a very broad audience today, which is great. Some of you might know a lot about plasma, and some of you might be quite new to plasma. Some of you might know that plasma is one of the key components in the N2 applied unit. But whatever level you're on, we can assure you that our speakers, who are experts in their field, will have some content that is interesting for everyone. And to say a bit about the webinar and the project, this webinar is hosted in relation to a EU Horizon 2020 FastTrack to Innovation project. And this is a program that encourages interdisciplinary projects across different sectors and by utilizing different technologies. And it also supports innovative concepts that has the potential to disrupt or create new markets. And that is exactly what we aim to do in this project through co-creation and collaboration between partners from different countries and across different sectors. The common objective is to commercialize a breakthrough innovation for upgrading livestock manure to an improved and sustainable fertilizer. And where plasma technology is one of the main components in this innovation. So the main concept is that we utilize plasma technology in a completely new application, namely on livestock manure. So the project is called Sustainable Manure, and by applying plasma in agriculture, we can create fossil-free fertilizer and stop both ammonia and methane emissions from manure at the same time. And this is the potential to significantly reduce the carbon footprint in agriculture. Studies have shown that in milk production, we can actually reduce the carbon footprint by 30%. So the impact can be significant. And the project consortium consists of 3 partners. We have University of Antwerp, Plasma Group in Belgium, who are leaders within the field of plasma. We have ScanArc Plasma Technologies from Sweden, who supply plasma solutions for industrial applications. And then we have Antwerp from Norway, who has developed the technology to produce fertilizer locally on the farm by only using air, electricity, and livestock slurry. And as the technology is quite complex and consists of different components, all partners are working together to achieve the same goals. And ScanArc is delivering the plasma technology in the project and also working to extend the maintenance intervals of the N2 system and also reducing the cost. University of Antwerp team is working on modeling the ScanArc thermal torch to find ways to reduce the energy usage. And Antwerp is delivering knowledge from field trials and pilot installations into the project, and also working along the other partners towards the objectives stated above. So while this project centers around the N2 system, it will create value and opportunities for all partners. And of course, the hope is that we will create new markets for N2 Applied and ScanArc, and also excel University of Antwerp's research and understanding in the field of plasma. So with that, I am very excited to hear more about from our speakers on what plasma is, and I hand the word back to you, Annemie.
Thank you very much, Helen. So our first speakers are Colin Omodrain and Ivan Sonev, and they are both PhD students on this project. So they are both paid on this project, and they will talk about what is plasma.
Hello, everybody.
Good afternoon. Thank you, Annemie. Yeah, so thank you, Annemie and Helen, for those kind words. My name is Colin O'Mora, and my colleague is Ivan Sonev. And as Annemie mentioned, we are doctoral students in the research group of Plasma in Antwerp. And we're here today to discuss what is plasma. So in terms of what we're going to be running through, I'll take you through what is plasma and then a very brief history of plasma. And then Ivan's going to show us a more contemporary usage of plasma, so both in industry and then also modern plasma applications. So probably one of the main reference points that we have for plasma is from Hollywood's Iron Man. So apparently Tony Stark developed a vortex arc reactor, which powers both his suit and the systems within the suit. We ourselves in Antwerp have developed a similar reactor, but unfortunately it's not quite powerful enough yet to power an Iron Man suit, but we hope to one day reach that goal. So as you may have heard before, or as you may have seen in the invite, plasma is commonly known as the fourth state of matter. And the other three states of matter that we're more familiar with are solid, liquid, and gas. And this description is based upon what is called the enthalpy of the system, or in layman's terms, it's more easy to describe it as either the energy or the temperature of the system. So the solid table that you're potentially leaning on has far less energy than the gas molecules that are bouncing around the room that you're sitting in. And then from that, plasma is much more high energy than any of the previous three states. So the main descriptor of plasma, or the main sentence we can use to describe plasma, is that it's a quasi-neutral, partially or fully ionized gas with macroscopic properties. So while this is quite a wordy sentence, we're going to break it down and try and analyze each part individually. So the first part that we need to look at is quasi-neutrality. So quasi-neutrality, the word quasi has origins in Latin, and it means to appear as. So when we say quasi-neutrality, we mean that the plasma appears to be neutral in that the positive and negative charges are balancing each other. However, when we go down to a very, very small scale, we can see that this breaks down, and we either have potentially more positive charges or more negative charges. So that's what our quasi-neutrality is. And then for the next part, we're talking about the level of ionization in the gas. So we can either have a partially ionized gas, and these are usually very cold. So as we can see here, we have a plasma jet, a cold plasma jet, so it's actually touching the skin, and we have a volume DBD. So both of these are relatively cold, so less than 40 degrees Celsius. So these often have applications in plasma medicine, as Ivan will allude to later on. And so we know that the body temperature is 38 degrees roughly, so you almost wouldn't even feel this on your skin. On the other end of the spectrum, we have fully ionized gases, which are, by comparison, relatively hot. And so the best example of this is the sun. But down here on Earth, we're also trying to produce fusion power through what is known as a tokamak. And both of these produce very hot plasmas. So the sun, the surface of the sun is roughly 5,000 degrees Celsius, but as we move towards the core, this obviously gets much, much hotter. And the image on the right, this machine is called a tokamak, and what it's used for nuclear fusion, which once again Ivan will allude to later on. And the temperatures within a tokamak, which we have here on Earth and they're being built, can reach in excess of 100 million degrees Celsius. And then the final part of this sentence that we need to look at is the macroscopic properties. So what this means is, as a bulk, the plasma has properties such as density and temperature that we can define. So just some examples of plasma in nature, both that we can observe with the eye and then further afield. One of the most common examples, or the most commonly known, is the aurora borealis, also known as the northern lights. And we can see here this image was taken from the International Space Station, and this occurs at the low pressure that's above the atmosphere. Another very common example that you may not have known before is lightning. So lightning occurs when an arc forms between clouds in the sky and the ground on the Earth. And then further afield, we have nebulae, which are essentially just large plasma clouds in outer space. So through all of these different modes, we actually know that more than 99% of the visible universe can be described as plasma in the fourth state of matter. So now I'm going to give you a very brief history of plasma. And as you can see, the field is relatively new, only starting in the 19th century, so about 150 years old. And it all started with the scientist William Crookes. So he discovered what he called radiant matter in his Crookes tube, which you can see down in the left-hand side of the screen here. And it was he who initially proposed this fourth state of matter concept. Then roughly 20 years later, a French scientist named Georges Claude displayed the first neon lamp in Paris, which is a type of plasma discharge that occurs in low pressure. Then in 1916, the scientist Christian Birkeland predicted that the interplanetary medium, such as nebulae, is actually plasma. And this harks back to our previous statement that 99% or more than 99% of the visible universe is made up of plasma. And in 1928, a very important point in the plasma field was when Irving Langmuir, he proposed the term plasma for what he was observing. And he coined this term because he noticed that the movement of the electrons within the plasma were quite similar to that he had seen in blood plasma. And then throughout his research in his career, he did many great advancements in the field, one of them being that he produced the first thermal arc using hydrogen gas. And then in 1942, Hannes Alfvén initiated the field of magnetohydrodynamics, for which he was eventually awarded the Nobel Prize in Physics in 1970. So I've taken you up to midway through the 20th century, so I'm going to pass you over to Ivan here, who's going to look at some more contemporary uses of plasma.
Hello everyone, I'm Ivan, and I'm going to talk about how plasma is employed in industry and the importance of plasma in industry. Why is plasma important in industry? Because it's involved in almost every industrial process in every industrial field, as you can see, from aerospace engineering to computer manufacturing to solar energy or textiles. So plasma has enabled our technology to progress enormously during the last century, and has given us all of these amazing luxuries like computers, phones. Through this, as Colin explained, we have a very wide variety of plasmas, and each of these plasmas can be employed in different types of industry. One of the most notable ones is the plasma etcher, which produces our very small processors in each of our mobile devices, each on our computers or phones. This device works by accelerating ions and removing material from a substrate layer. And by this, it creates a very, very small, very, very tiny transistor, which actually is the brain of your mobile phone and the brain of your computer. The same process, but by changing the parameters, could be employed to grow crystals on a substrate. This is called the plasma-enhanced chemical vapor deposition. And this is more or less similar to the setup that we saw before, but in this case, you can grow very specific crystals, such as diamonds. And this makes it very interesting because in all of our cutting saws, all of our, let's say, Dremels, we have these diamonds which help us cut very hard materials. And it's very highly probable that when you buy something for the store, it's produced by this technology, which is the plasma technology. So plasma also helps to bring sci-fi to life. As you know, for the past few years, Elon Musk has promised to bring people to Mars, but using the normal way of propulsion, we cannot do it because it's not efficient. So scientists developed these plasma ion thrusters, which actually create ions that accelerate our space vehicles in space. They are used a lot in satellites and for a long time, and because of the space technology needs them, they are the only way for us to travel from Earth to Mars. So plasma enables also space travel, which is extremely interesting. In a more practical sense, let's say down to Earth, plasma can modify all kinds of surfaces, including metal, glass, ceramics, all kinds of polymers that are sensitive to temperature or sensitive to some chemical active species. And you can see for the far right picture, when you treat a boot with plasma, and put it into water, the water doesn't penetrate inside the boat. And this is because the plasma is changing the surface of the material in a way that we can control, and it can benefit us a lot. You can see that this can also be used in manufacturing lines to modify materials, to modify plastic bottles, or to modify textiles. And it's most likely that every package that you buy in the store is also treated by plasma. So plasma is extremely broad. But one of the most important, maybe the most important application of plasma is that if you say that plasma makes you more beautiful, that is actually true. And by developing these small plasma devices, small technology, they're kind of are being employed right now in the beauty industry, where the beauty industry is claiming that this also has an anti-aging effect. So because plasma can be created in a lot of conditions, it could be cold, it could be hot, it can also be used to apparently make you very beautiful. So plasma is also a field of science. So we are, as Helen explained and Colin explained, there's a research in plasma and there's the plasma application. And some of the technologies have not yet transitioned to the industry. So now I'm going to talk about a few of those. One of these technologies is plasma medicine, which was created in the early 2000s. And this utilizes these cold plasma jets that Colin was talking about. And it could be divided into main fields: dental plasma medicine and general plasma medicine. While dental plasma medicine I find most interesting because I'm very afraid of going to the dentist, and this provides a non-invasive way to treat dental illnesses like cavities or certain type of infections. In the more general term of plasma medicine, we can see cancer treatment, very interesting application and new applications of treating rare diseases or diseases that are hard to cope with the general drug and general state of the art of medicine. Probably the most famous device is the fusion device. So currently we're producing most of our energy with fission. So in fission, we're splitting heavy elements to create energy. But if we can fuse very light elements, we can also create a lot of energy, which is much cleaner than fission energy. For this, we created these artificial suns, very big machines, which are called tokamaks. And we are trying to replicate the conditions in the sun so that we can create our infinite source of clean energy. There are several devices that were created. The tokamak is the oldest one and most investigated one, but on the left we can see the sterilator, which is very much more complicated. It has complicated shapes, and both of them are created in a way so that we can control the plasma and make it work, make it reach these specific temperatures more than 100 million degrees Celsius. Another very interesting, which is a recent discovery of plasma, is that we can process meat or different type of agricultural products with plasma. So why do we need to process meat? Because to preserve meat fresh, we need to treat it with chemicals. And some scientists found out that if you treat the meat with plasma, you can remove the toxic chemicals, but keep the meat fresh and firm and preserve its shelf life longer. Also, by treating different types of fruits, you can increase the antioxidant activity of these fruits. Or if you treat the seeds, you can make the seeds grow faster and produce more yield. So the agricultural applications of plasma are proving to be very efficient and very clean for the environment. In summary, plasma has helped us develop society a lot because of the technology that it enables, and because it basically changed the way we're living. Every seventh manufacturing technology in the world is currently employed by plasma. And here in the University of Antwerp, we're trying to bring or helping to bring the newest technology into the industry right now. Thank you.
Thank you very much, Colin and Ivan, for this very nice overview. I remember especially that plasma can make you beautiful and that it can solve your problems if you are afraid of the dentist. So then our next speaker is Philip Angwald. He's a development engineer at ScanArc, and he's also project manager for ScanArc in this Horizon FTI project. And the title of his talk is How Plasma Tech is Enabling the Circular Economy. The floor is yours.
Thank you, Annemie. Yeah. Yeah, hello everybody. My name is Philip, and like Annemie said, I'm an engineer at ScanArc, and I'm going to talk a little bit about how plasma technology is enabling the circular economy. And I think it's a good idea to start off by looking at what a circular economy is. And I think a good way to describe it is to talk about what it isn't. For example, if you consider the lifetime of a coal mine, what you have is you have coal in the ground, you build your mine, you start to extract the coal, and along the way you have massive amounts of waste, emissions, and pollution.
Can I just interrupt?
Yes,
we are not seeing your slides.
Oh. How about now?
Yeah, not yet in presenting mode, but yeah, perfect.
There we go. So yeah, the coal mine, you extract the coal, you have a lot of waste and pollution. Eventually you extracted all the coal and you burned it, and now you shut down the mine. So that's a very linear economy, while a circular economy is all about reducing the waste, recycle and recover your materials, and you use sustainable supply chains, and you use your resources continuously. So if we look at some of the markets where plasma technology is applied today, you have, for example, in the metal industry, you can use plasma to recover valuable materials and metals from the waste. By treating it with plasma, you can recover copper, zinc, lead, and silver, and you can recycle those materials. In the energy industry, you can treat your waste from incineration plants with plasma, and you turn that waste to value. And in the building, construction, and steel industry, you can use plasma technology to electrify your furnaces and reducing your CO2 emissions drastically. And then, of course, we have agriculture industry where N2 Applied is working to develop their process. And we will hear more about that from Luciano at N2 in a few minutes. If you would like to know more about this and what we do in these sectors, then I encourage you to go to our website. But certainly we can see that we use plasma technology already to recover, recycle, we treat waste, and we electrify industries. So already we are working to enable the circular economy in some way. And if you look at the global trends, they all seem to point to electrification. The cost of renewable technologies have been declining for years, and the projection is that they will keep declining. On the other hand, fossil fuels are becoming ever more expensive to use. So we see a lot of sectors are now looking to update the processes, either to comply with goals and regulations or just to stay competitive. They want electrification. And that's where we at ScanArc come in. A little bit about ScanArc. We were founded in 1989 in Hofors, Sweden, where we still have our offices and workshop today. We emerged from metallurgical industry, and we now have more than 30 years experience in the field of plasma technology. We work mainly with innovative projects and industrial implementation of plasma, and we produce our products in-house. So our vision is to deliver heat where it matters. We want to become #1 on fossil-free heating, and we want to be a reliable R&D partner. So our research and development service is to offer the possibility for customers to come to our pilot plant and build a scaled-down version of their process, which we run on plasma technology. We evaluate the results and show how well the process runs on plasma, and then we can design, develop, and adapt the torch to suit their process. So if we look at the plasma torch itself, which is the main product of ScanArc, you have an example to your right here. It's a non-transferred plasma of tubular design. You have copper electrodes, which are water-cooled, and we use a stabilizing swirling gas flow. And we can offer this torch in a power range from 10 kilowatts to 8 megawatts. And basically any process gas can be used, but air and carbon monoxide is common. And if we look inside of the plasma torch, this is a schematic of the inner parts. You have two main electrodes, which is the upstream and downstream electrode. We inject gas at multiple points, and we use a voltage to the upstream electrode to ignite the electric arc to the downstream electrode. And the arc then in turn heat the gas, which exits at a few thousand degrees. So when you have renewable electricity in abundance, at least some of the time, the problem is that most industries don't run on electricity. They run on natural gas or maybe oil. So you need an intermediate step, which is where you can use the plasma torch. And that is a crucial part of the chain to enable a circular economy in the future. And we've seen great progress. We have, for example, a company which came to ScanArc 30 years ago to evaluate if they could electrify their process. And they had good results, but the price of electricity was too high at the time to motivate the change. But since then, the electricity price have been declining. So last year they came back and they had good results once again. They found that they could reduce the amount of coal in their process by 90%. And on top of that, they can run it on electricity, hopefully renewable electricity, which allows them to stay competitive. And another success story is hopefully N2 applied, which we will hear about more in a few minutes. So that's it for me. And if you have any questions, then please put them in the chat or contact me directly. Thank you for your attention.
Thank you very much, Philip. This is the perfect transition and introduction of our next speaker. And our next speaker is Luciano Patruno, and he's the R&D manager at N2 Applied. And he will talk about upgrading organic waste with plasma.
Good afternoon. Can you hear me?
Yes.
Very good. Good afternoon, and thank you for the introduction, Annemie. I want to start by showing you two pictures with two tractors.
So you also have to share your slides.
This is not in sharing mode.
No.
Let me see.
I believe I can see the slides.
I can see the slides too.
Oh,
yeah.
Oh, at my end as well.
Great.
All right. Then it might be that it takes a while.
Now I see them as well.
Load. Very good. Then again, I start by showing you two pictures of two tractors spreading fertilizer in a field. And why do farmers do this? Well, fertilization is actually necessary to bring back nutrients to the soil and to get the same yield year after year. And you might know that nitrogen is the key nutrient for plant growth, and livestock manure, or slurry in liquid form, as we call it, needs to be spread out to the field. And by that activity, we are losing a lot of nitrogen, and it's difficult to use precisely, and it has challenges in application. So on the other hand, in the picture to the right, the chemical fertilizer is widely used. It's based on fossil fuel, and it does contribute to climate change. So that being said, chemical fertilizer has helped in growing plants and producing food up to 40% of what we have today. So how we solve these issues? Well, we at N2 Applied, we enable farmers to produce their own fertilizer by using only 3 ingredients, and those are the slurry or the manure, air in the air that we breathe from, and electricity. Those 3 components are combined in the N2 unit to produce what we call the NEO, or nitrogen enriched fertilizer. And the technology, it's based on what Ivan and Colin were talking at the beginning. In 1916, there was a famous Norwegian called Birkeland, and he was working with plasmas and how to create usable nitrogen out of it. And the fun fact, if you are visiting Oslo, you can see the reactor that he used in the parking lot at the Technical Museum. So we have taken the Birkeland process and we have taken it one step forward, improving it to be more efficient. So we have this plasma torch in the middle, and the plasma torch is provided by the technology of ScanArc. That plasma takes the regular air and decomposes the atoms of nitrogen and oxygen and makes them active or reactive, so that we can create the very valuable nitrogen components, or nitrogen oxides, these NOx components. And these gases are then absorbed into the slurry in the absorption system in our machine, so that we create this nitrogen-enriched organic fertilizer, these NEO compounds. And And I said that through our process, we are adding nitrogen and we are making it more environmental friendly. And that has a very simple explanation. If you take untreated slurry, it does contain nitrogen, both in an organic nitrogen and in the picture that is shown in the brown bar, the top one. And then there's also ammonium that is present in the untreated. But up to almost half of that ammonium present in the untreated can be lost as ammonia to the environment. So in reality, there is not that much nitrogen available in a slurry. So when we treat it with our process, we manage to capture and to lock that part of the ammonium, and in addition, we add nitrates to the fertilizer. So in that sense, we have all the nutrients that a plant needs in the sense of nitrates and ammonium, and the slower nutrients in taking into account the organic nitrogen. And if you see the picture, we are doubling the content if you think about the content towards the untreated one. And if you even don't consider the part of the organic nitrogen in the fertilizer, then we are up to 4 times more than what it could have. And don't take my word for it. You can also refer to independent research institutions that have verified our statements. And in particular, I can mention the Research Institute in Sweden and the ADAS Institute in the UK. We have both conducted emissions tests, and we see that our process, the NEO process, really reduces the emissions. both for ammonia and for methane. So this is very interesting, and it's not limited to Sweden and the UK. We have, throughout the history of the company, conducted field trials all around the UK, all around the Nordics, and we are now starting also in mainland Europe. We have had several trial partners, and they all conclude to the same: we are cutting emissions. And this is also a picture that shows the benefit of applying NEO. And let me spend a little bit more time and explain it to you. Basically, green is our favorite color. We like grass, and we like grass to be green. So this is a field trial where we conducted different plots that were fertilized with different fertilizers. To the left, there is a plot that we used chemical fertilizer. That is the industry standard at the moment, and then we have used other types of fertilizer, both based on slurry, and towards the most right, then you see NEO. And there is a clear evidence that NEO is as good as chemical fertilizer. So we are also matching this 40% yield increase. Benefit, we are doing it without the emissions. So we provide an attractive value proposition for farmers. We are increasing the nitrogen value of the slurry, and that leads to higher crop yields and less emissions. The added nitrogen to the slurry, it ultimately becomes more nitrogen that is available for plants. And since we produce a very precise fertilizer, it can be used in precision farming. So we know how to apply the right amount of fertilizer at the right time. It's a machine that it enables local production, so it gives the independence to the farmer to be self-supplied of the nitrogen that they need. And as I mentioned before, we eliminated the emissions, making it a better fertilizer with lower environmental impact. So to conclude, and in a way to sum up, we are improving the sustainability of food systems, and this is our way to contribute into making the world a better place by reducing the greenhouse emissions, reducing the use of chemical fertilizers that are based on fossil fuels. We also increase the crop yield and improve the use of the nitrogen. And in addition, we are reducing the ammonia emissions and cutting down the smell of or the odor of the fertilizer. So that's pretty much everything I wanted to say. I leave you with a picture of a tractor spreading fertilizer on our facilities here in Norway. And thank you very much for your time.
Thank you very much, Luciano. So it's good that this can also reduce the smell. So this is something we can always appreciate, I think. Yeah. So with this, I would like to thank all our speakers of this seminar session. And then, yeah, we have the Q&A session. So all the lectures are open for discussion and asking questions. I see no questions in the chat. Ah, there is a question already. Yeah, Kure?
Gunnar, I'm working at N2 Applied as well as I'm a dairy farmer. In the presentation from Philip Angwald, you mentioned torches from 10 to 8,000 kilowatts, if I remember correctly. And I had a question both to you and also to Colin and Ivan. Is it easier to make the big ones most efficient, the 8,000 kilowatts, or the 10 kilowatts, or doesn't the size matter in this case? Does matter in other cases, but how is it when how is it with plasma and the size?
Well, maybe Colin and Ivan can answer it better, but if you're talking about just igniting the arc, then it doesn't really matter that much on the voltage as long as the other parameters are in balance with the voltage, so to speak. Maybe you and Colin and Ivan, do you have anything to add?
I would say it's a delicate balance. So if you put more power, this doesn't mean that it's going to get better. And this is why University of Antwerp, what University of Antwerp is working on. So it's a part of our research to find out how to scale such plasma reactors.
Indeed, that is true. Was this answering your question?
Yeah.
Okay.
Still, possibly a question to still be researched then, if how much the size matters. But as I interpreted you and understood it, it doesn't seem to be so important in this case.
Okay. Is there another question?
I saw there was one question maybe in the chat that you can have a look at, possibly.
And now I see the chat. I couldn't see it. Let me see. I see a lot of history in the chat, but
there was one question, I believe, that we got an answer from Rune, and then just another question popped in. Has any measurement been made of NOx emission after field application on crops? That could possibly be for you, Luciano.
Yes, I can answer that. We have done measurements both in pod trials, so small scale, and also in large applications in field. This is done with kind of a wind tunnel that is placed on top of the field, and then air is sampled out of that, run through either a mass spectrometer or any other device to measure the NOx composition. Yes, we have done.
If there is another question from the chat, for one or another reason, I can't see it because apparently I'm not a member of the chat. That's the message I get. So maybe Helen, you can...
Yes, no problem. There was 2 or 3 other questions here, actually. So first one was, how much of N2 applied fertilizer is used in comparison with commercial fertilizer? Is it more or less? I guess maybe for Luciano to answer as well.
Yes, I can answer how much our fertilizer is used. So our fertilizer is when it comes to application, if that is the question, we match the nitrogen content, but then in the end the volume is less than what is now applied, because we have more concentrated nitrogen in the liquid. Second question is, what is the price of the N2 fertilizer compared to the best commercial option? Well, I'm not sure there is a price fixed at the moment, but if you take it as something that can be produced by the farmer, then it's down to the cost of electricity. And if the farmer is equipped with renewable electricity or electricity that they can produce on site, then they are not paying for electricity. They're of course not paying for air, and they are not paying for the slurry because that's a waste they have from the field. So the price of the fertilizer itself, tending to nothing.
I see there is a question from Yang Fang Li, who raised his hand or her hand.
Yes, Yang Fang from CIDA. I have a very simple question. So when you're talking about you can operate the plasma torch or whatever the plasma system with 10 to 8,000 kilowatts. So have you tested what's the effect to the lifetime of the system? So can you operate, for example, for 1 year, half a year, 1 hour, 2 hours?
But we've seen examples when we operate at 2 to 3 megawatts up to 800 hours or maybe even a little bit more. So it's about 800 hours. That's a good case. There's also examples of shorter time periods.
Okay, thank you.
Helen, maybe help me if there's a question in the chat.
Sure. There were a couple more, I believe, here. Let's do the last one first, maybe. What would you consider a bottleneck disadvantage for plasma technology or plasma reactors in view of electrification in the chemical industry? Would that maybe be for Philip or Colin and Ivan to answer?
I don't know much about the chemical industry, but some disadvantages of plasma torches is, of course, you need a very stable and possibly large power supply. If you have megawatt scale, you need to have a suitable grid connection as well. And as I said, you need to perform service in a regular basis, 800 hours. Around 800 hours, you need to disassemble the plasma torch and perform a service before it can be operated again. So that's a few disadvantages.
And I guess in terms of our side in the University of Antwerp, one of the large avenues of research that we explore is greenhouse gas conversion. So I'm not sure if it's necessarily the chemical industry we're thinking of, maybe thinking of more producing chemicals, but yeah, so on that side of things, there's large potential for greenhouse gas conversion, and we're deeply entrenched in the investigations in Antwerp at the moment.
Yes, great. And there are also then 2 other questions here, I believe, for Luciano, which is, I guess you maybe answered one of them, but one question is on how much NOx is produced.
You are muted.
Sorry. I was just typing an answer to Gary. The NOx production emissions from field application, I guess you meant that's related to the previous question. That is on par to the chemical fertilizer, but we are working on improving that, so it will be even less than that. And there's also another question from Marchetti. It says perspective of farmers accepting this fertilizer. Well, we are conducting these field trials, and those are together with large agronomic either institutions or small farmers. And the idea is to show that the fertilizer has exactly the same yield with the benefits of the emissions and the benefits of the cost. So the perspective is that it will be accepted with no challenges.
Great. And then there was one last question here popped in. I studied that swirl flow is used to avoid the erosion of anodes, but have you done any analysis about how much swirl to be used? Possibly Philip or Colin.
Yeah, well, we performed practical tests and tried to find a good amount of swirl flow. But I think maybe Colin and Ivan knows more about the theoretical side of things.
the faster we can make the arc rotate, the better for the electrode. So you can do this either with swirl flows or magnetic fields, which I believe ScanArc is employing in their more powerful arcs. So if the arc is rotating faster, the erosion on the electrodes will be lower.
Great, and there were no more questions in the chat as far as I can see.
Okay. I see that Yang Fan Li still raises his hand, but maybe it's still from the previous question, or do you have another question?
You know, I have no more questions, thank you.
Okay. I have a question for Luciano. I think you mentioned somewhere that also the methane emission was reduced. Can you explain why?
Yes, maybe that's actually a question that can be answered by one of our agronomists, if Magnus or Nick are online. Nick, I see you there.
Yep. Yeah. So it's a twofold benefit or effect. So the first one is the pH reduction prevents methane formation and emission, and also the fact that there's nitrate and nitrite to prevent highly reducing conditions and methanogenesis from microbes in the slurry or the neo. So both ends there will prevent methane loss, and we have quite a few trials where we've shown pretty much complete elimination of methane loss from a plasma treated slurry. So.
Okay, thank you.
Thank you,
Is there another question from people attending? Otherwise, I have a question for Philip. I saw in one of your slides that the main gases of the ScanArc reactor are, you mentioned air, for instance, but also CO, if I'm right. Can you explain for which application this is being used?
I know they use it at a company called Scandust in Landskrona in Sweden, but I'm not really too familiar with their process. So I'm afraid I don't know, but I can find out.
Okay, but it was not a mistake. It was not CO2 to reduce CO2 emissions, so it was
no, it was not a mistake.
Yeah. Is there another question from somebody?
There was one more here in the chat, building on Luciano's answer, I believe, but how does the pH affect the methane loss? Or Nick?
Yeah, it's quite well documented in a few different papers. I'm trying to find the quick answer for you now, but yeah, that's fairly well established that the pH reduction via sulfuric acid, nitric acid, or by neo treatment can reduce pH emissions, methane emissions. But in addition, we have the prevention of the highly reducing emissions with the nitrate presence as well. But yeah, sorry, I haven't got a quick answer on the pH, but it's say well documented.
And then one last one on asking when the manure is plasma treated, directly before it's spread or on the field.
Let me understand that. When is the plasma? So the manure is treated independent on when is the application going to be. So it can be treated and stored and then applied afterwards, or it can be treated on the go and applied immediately. So I don't know if that answers the question.
Are there more questions in the chat, Helen? Because I can't. I see there's a question by Dijke Hatcher. Please go ahead.
Yeah, hi, I'm Dijke. I'm working inside AS near Stavanger. Getting to the methane emission or the reduction of the methane emission, is it that the formation of methane is prohibited because of the low pH and the and the nitrates present, that they just reduce the activity of the bacteria in question, or are these affecting chemically, these substance and the pH affect chemically the methane?
So the nitrate presence is to do with the nitrate acting as the terminal electron acceptor. So while that's present, there's no drop in reducing conditions in terms of the electrochemistry, and there is a inhibition of microbial activity as well.
I saw there was a question from Mats Lindström, but he removed his hand again.
There's a question on the chat.
Okay.
It says, how big or small farm in acres is it feasible for an N2 system today? Well, we are targeting a system that can handle slurry, that it's coming from around 200 cows. So that's more or less a target, 200, 250 cows.
I believe we probably need to stop the session there. I see, yeah. I think we'll close the chat there, and then you can close the session.
So I want to thank all the speakers again for the very interesting presentations. And I thank you all for your attendance, and I hope you found it interesting, and you can follow actually the progress on our project on the FTI project website. So I thank you all for your attendance, and have a nice day.